So in order to talk about security, we need to first introduce a very popular notion in cryptography called one-way functions. Okay? And the security of the scheme will be based on one-way functions. So we're going to talk first about one-way functions, and then we're going to see what is the security of a public key encryption scheme that's going to be based. It's going to be similar to the INCPA definition for symmetric key encryption, but actually much simpler. We'll see that it's much simpler in the public key setting. Okay. So one-way functions are functions that are easy to compute in one direction, but hard to compute in the other direction. So a one-way function, so a function f is one way if we have two conditions. Given x, it is easy to compute f of x. Okay? And 2, given y, it is hard to find any x, so not necessarily the x that produced the y, but any x, such that f of x equals y. Okay? And what do we mean by easy and hard? Well, remember that we model humans and machines as polynomial time algorithms, right? So anything that's computable in polynomial time is easy, and anything that cannot be computed in polynomial time is hard. Okay, so easy means that you can compute it in polynomial time, and hard means that there's no polytime machine or algorithm that can invert this function. Okay, so the function only goes one way. So, for example, a very intuitive example is making hamburger from a cow. You can make easily the hamburger from the cow, but you can't get the cow back from the hamburger. So that's a one-way function. Okay. So let's see some examples and let's see if they are one-way functions or not. So let's take f of x equals x. Is this a one-way function? No. Why? Yeah, exactly. It is easy to invert. So no, easy to invert. All right. Another function is f of x equals 1. Is it one-way function? Exactly. So this is a bit tricky. So basically, it's not a one-way function because the definition of one-way function says that it's hard to find any x that leads to the y. So the y here is going to always be a 1 because that's the only output of the function. And it's super easy to find some x that leads to that 1, any x. Now, it's true that it's hard to find the original x. Let's say I take some x 10, or some random x, and then I compute f of x and I get 1. It's really hard to go back to the original x because 1 doesn't carry any information about the original x. But that's not the definition of one-way function. The definition of one-way function is that you can't find any x that leads to 1. And in this case, all x's lead to 1. So it's not a one-way function. Okay? So it's a bit tricky in that sense. Okay, so it's no. Any x leads to 1. All right. So let's try some other one-way functions. So we're going to take f of x to be some block cipher for which we chose a random key, and we apply the x to it. Is this one-way function or not? So we learned about block ciphers last time, such as AES. We use them in building symmetric key encryption. But the question is, are they one-way functions? So the answer is that it's not a one-way function because you don't know k. So in this situation, the input I'm referring to for the definition of one-way function is x. Okay, so I'm not going to try to get the k. I'm going to try to get the x. The question is, can I, given the output of the block cipher, obtain some x that led to that output? Okay, so you can think of e sub k as one function. Okay, you can think of the key hard-coded in the block cipher. The question is, can you invert the block cipher? Exactly. So the block cipher's definition, security guarantee, says that it's indistinguishable from a random permutation. Okay, so now if I give you a random permutation, so you have this random permutation R that maps some x to a completely, random value. If I give you this random value, it's really hard to find the x that led to that R because it's random, right? It's supposed to be indistinguishable from a random function. Okay, so basically E sub k is indistinguishable from a random permutation. If you could invert E sub k, then it would not be a random permutation. Why? Let's say someone gives me a value y, and I'm supposed to decide if it was output by the block cipher or if it was output by this random permutation. Well, if I could invert E sub k, I would try to invert this y. If I get an x such that I can compute E sub k of x and I get the y back, then I know, yeah, this is from the block cipher. Because I could not invert the random permutation. Okay, so if E sub k were invertible, then it would not be a random permutation. So the answer is yes, because it is indistinguishable from random permutation. Any question? Yeah, you're assuming that your function is exactly this whole block cipher with the key hard-coded in it, and you don't have the key. You just have the function as a black box, and the question is whether you can inverse it. Yeah. And I mean, if you think about the PRG David told you about last time, well, this PRG was a block cipher that was taking as input key and IV. If you're able to invert that, then you'd get back to the key, and that's problematic. Okay, so we clearly don't want block ciphers to be invertible, so they are one-way functions. Any question on one-way functions? Yeah, back there. Yeah, that's a good point. So I'm going to repeat the question because the people from the webcast asked us to repeat questions. So if block ciphers are not invertible, how do we decrypt? That's a very, very good point. So without having the key, they are not invertible. But if you have the key, then you can invert. Okay. So here, I was treating E sub k as one black box where you don't have the key. So don't have key. So because you don't have the key, you can't invert it. But the moment you have the key, you can invert it. Okay, so the function E in E by itself is invertible, but the E sub k is not.